Okay, let's come to our next section, which is called normed spaces. In the previous section, metric spaces, our set X that was underlying could be pretty much anything as long as it was not the empty set. For example, it could be like the set of all cities in Germany, and the distance function could just measure the distance from city 1 to city 2 along the motorway. Now X gotta be something with much more structure. Now X has to be a vector space. Do you remember what a vector space is? This should be linear algebra 2, second semester in your bachelor degree. So in a vector space you have the set X together with two operations. So you have an operation plus that can take two elements of X that from now on we call vectors, and the result will be another vector element of X. Then you have multiplication, but not multiplication of two vectors, but rather than that of a scalar. We often call them alpha times a vector. And you have to say where little alphas are coming from. So they come from, well, what mathematicians call a field. And let's not go into too much detail, because for us we only have two fields that we are interested in, and one of them is R and the other one is C, the set of complex numbers. So alpha is a real or complex number, and we can multiply them by them. So in a vector space you have things like a zero element. You don't have that in the set of cities of Germany. Zero element is the one that under addition doesn't change anything, so it's the neutral element of addition. Then you have a whole lot of rules how plus and alpha times play with each other and are compatible. And so after all, I think a vector space is defined by something like 8 or 9 axioms or rules, just like we had 3 rules for a distance function. Here you have 8 or 9, and you did them in linear algebra too, so let's not repeat all of that. Okay, vector space. So examples, R to the n would be a vector space over the real numbers. So the little alpha would have to come from R or C to the n. What's happening here? C to the n. So in this case, the little alphas come from the complex numbers. What else? Well, you could have maybe the set of all continuous functions on the interval 0 to 1. We saw them in the very first lecture. What do you have to check? Well, you have to check whether or not the sum of two continuous functions is again a continuous function, but analysis says so, yes. And you have to check whether 3 times or another multiple times a continuous function is still a continuous function, and yes, that's true. The zero element in the set of continuous functions would just be the function that is constantly equal to 0. If you add it to another function, you don't change that. Okay, and one by one you can check all the little axioms and find out, yes, also that is a vector space. Yeah, we will see lots of others. So what is a normed space? In a normed space, you even have more structure. You do not only have plus and alpha times, you have one more feature, and that is a norm. That's where the name comes from. Okay, so that is worth a new definition. x together with plus and alpha times, and this thing that we call a norm is a normed space if, okay, and now you need some properties that essentially make sure that the new kid in town, which is the norm, plays nicely with the other kids that have been here before. One of them is plus, the other one is alpha times. Let's see how that can be written down. So the first condition is that, well, this is actually not compatibility with the other two operations. This is what we call definiteness. So the norm of an element x gives you 0 if and only if x is the 0 vector that, like we said, you always have in every vector space. Second condition, now that says that the norm has to be compatible with alpha times, in the following sense: the norm of alpha times x is, well, I could say alpha times norm x, and you always say no, that's not true, you need the modulus of alpha times norm x, okay? Absolute value of alpha times norm x, and we know that. And the third property now is about compatibility with addition, and that says that the norm of x plus y, so now you're adding two vectors, is what has something to do with norm of x plus norm of y, and this is something that we've seen before. Okay, and we are not expecting equality here, but rather than that we're expecting inequality in this direction. And just like for the third property of a metric, of a distance function, we are calling this here the triangle inequality. This one we are calling definiteness, and the second one I have no idea what name that one has. Maybe I've probably never used one. Okay, so again, these conditions need to hold not just for 1 or 2 x and y, but of course for all vectors x and y and all little alphas from your field. Let me call it f, which is an element of this two-element set that contains R and C. Okay, what are we defining here? The word normed space. Let's also define another word, which is norm. In that case, this map, which takes an element x and produces a real number, is called a norm. Okay, so of course we know norms of vectors for elements of Rn or maybe even Cn, but here we claim that the concept of a norm can be taken to a much more general level of arbitrary vector spaces. Well, for norms of vectors, we are used to interpreting them as the length of that vector, as long as you can somehow geometrically envisage that vector, which perfectly works in R2 or R3, not so much in R17. Nevertheless, we are used to the fact that the length of a vector is positive or possibly 0, which happens if and only if it's the 0 vector. That's what property 1 says. Just like in case of the definition of a metric, one might again ask, how about property 4? How do we know that norms are always greater than or equal to 0. Why is it impossible to have negative norms? Of course, that would be counterintuitive, but this definition is not about intuition, it's about mathematics. And we want to know whether property 4 follows from 1, 2, and 3. And you can guess that yes, it follows. So let's make that remark. Property 4 follows from 1, 2, 3. And the proof is like we did this before for metrics. Want to see how? Let's play around a little bit. Okay, let's try take the norm of an element x and we add to it the norm of the element minus x. Of course, we know that minus x is just minus 1 times x, so that by formula 2 this is norm of x plus modulus of minus 1 times norm of x, where of course the modulus of minus 1 is just a 1, so we get 2 times norm of x here. But on the other hand, we have by triangle inequality, property 3, that this is greater than or equal to the norm of x plus minus x, all inside the norm brackets or signs, where of course x and minus x cancel each other and give you the 0 element. Now that must be the norm of the 0 element, and by property 1 that is just 0. I mean, I guess you can somehow recognize the proof that we had for metrics and the corresponding property there. So if you divide everything by 2, you see that the norm of x is always greater than or equal to 0. So again, it's perfectly fine to look at properties 1, 2, and 3, and negative values of the norm are already ruled out by these, as we just saw. Unlike in the case of the metric space, we have even one more simplification to make in this definition. Let me write that down as a next remark. Number 5, in condition 1, it is enough to demand this direction. So saying that the other one follows automatically. Okay, again, we can prove that, and we should prove that. So to see that this follows automatically, check the following. So if x is the 0 vector, then its norm is equal to 0. How can we see that? So look at norm of the 0 vector. And now you can say that the 0 vector can be written as 0 times any vector that you want, for example a 0 vector or any other vector. We don't even have to say what vector x that is here. Okay, and then just use number 2 to get the 0 out as modulus 0, which still is 0, and then you can see that no matter what your vector x is, the result is going to be 0. So indeed, this direction is always automatic from property 2.